Hello, class. It's a bit later in the day. I just did lab 6, which I think in it I called it lab 5, but this is lab 5. This is going to be a lab looking at stress strain curves, uniaxially applied forces trying to pull a tensile member apart. And to set this up, I want to go to this page. It's actually a YouTube page. And virtual laboratory strength of materials. This is more or less a demo for a virtual laboratory that a university, let's say, didn't have the type of setup that Wentworth has, where you go in and you use the laboratories, could do something similar to this and then pay these guys a whole bunch of money. But what I did was I looked at the video, and the video actually has a lot of informative stuff, so that for this one time when we're doing this, we can really use this. So let's look at this right now. We've got a tensile specimen in there, and it's low carbon steel is what they chose. So I'm going to give you the specifics of this, but let's just watch this demonstration for a second. I'm going to stop it when it gets past the yield point and goes back to the graph on the screen. It'll just be a second. It's going to look at it here for a second, then it's going to flash back to the screen. There you go. I'm going to stop it right there. Now that has all the information that we really need to do the lab right here. You can see that it has gone, if you look at the bottom, that's traverse displacement delta L. So that would be your, delta in the equation. Delta equals PL over AE, right? Delta equals PL over AE. So the delta here, you can see that if each one of these, if we've got 4 different blocks and that makes up 1.33, doesn't that mean that it's 0.33 per block, right? So as you can see, this has only gone 3 of those grid blocks up at the top, and that means that it's gone 1 millimeter. So let's just put this all together now. So let's start writing things down. I'm going to give you some information too, and I'm not going to write it down. I want you to listen to me, listen to the video, take notes, just like you would when you're working a regular engineering job, right? So let's look at that point on that graph. That point says that the extension, delta, is 1 millimeter. And it says that the force required in newtons to produce that delta is approximately, if we look over here, that's about 6,700 newtons, isn't it? So we've got our first 2 variables. The extension is going to be 1 millimeter. The force applied to get at that 1 millimeter is 6,700 newtons. I'm going to tell you right now the modulus of elasticity for low carbon steel is 100 gigapascals. The modulus of elasticity, which is really the slope of the line on the stress strain curve, right, is 100 gigapascals. Also, we're going to say that the maximum stress for this low carbon steel is going to be 500 megapascals. Okay, so 500 megapascals is the maximum stress, the yield, I shouldn't say maximum, but the yield stress right when it finishes, right at that point, right where it finishes the linear elastic range of the stress strain diagram, or in this case, what we're looking at is a force displacement diagram, aren't we? And we know that if I wanted to turn this into a stress-strain diagram, I'd have to take the y-axis, the force, and divide it by the cross-sectional area. And to make the x-axis strain, I would have to take the delta L and divide it by the original length. And this is what I want you to do for the lab. I want you, taking that information that we've got so far, to tell me, what does the original length come out to? Two things. I want A, what is the radius, right? Using the information that I gave you, what is the radius of the tensile specimen? That's the first thing. And the second thing is, I want to know the original length of that tensile specimen. So what is the radius of the tensile specimen if the maximum shear stress, or the maximum normal stress, is 500 megapascals, and I want to know what the original length, right? Now you're probably looking at the virtual lab and you're saying, oh, that looks like about 3 inches, maybe 4 inches, I don't know what it is, but that's not what the original length is going to come out to be exactly. And that's why I sort of figured this out when I did it, but it's sort of, but get an answer. I want you to, knowing Hooke's law, sigma, normal stress equals Young's modulus times strain, and putting all of that together, you should easily be able to do that with that information I've given you. I'm going to give you that information one more time. The maximum normal stress for low carbon steel is 500 megapascals, right? And the modulus of elasticity for low carbon steel is 100 gigapascals. We've taken off here on the force elongation graph 6,700 newtons, right, is our force, and that allowed us to extend that 1 millimeter. So 1 millimeter is our delta, or delta L. And that's the two things that I want you to find out from this lab. I want you to find out what the radius, the original radius of that tensile specimen was, and I also want you to find out the original length. And it's going to actually come out a little bit different because I've changed these things so that it will, right, so that I can see what happens. All right, and that is Lab 5, and then I've also already got Lab 6 done, which I think, as I'm talking through the torsion lab, I call it Lab 5, but it's really Lab 6. All right, those two things should be up there. All right, back to work. I'm going to stop sharing this slide, and that is it for what is really Lab 5. And then, like I say, the torsion lab is going to be Lab 6. Okay.